Welcome to the course on an introduction to information theory. So in this lecture we are going to talk about an iterative algorithm to compute channel capacity and rate distortion function, and this is known as Blahut-Arimoto algorithm, named after these two scientists who independently came up with this algorithm. So first we will talk about this algorithm in a general setting, and then we will be talking about alternating max optimization algorithm, and then we will talk specific about this Blahut-Arimoto algorithm. In particular, we will talk about how we can use this algorithm to compute channel capacity and how we can use this algorithm to compute rate distortion function. Now for this lecture we are going to use the book by Raymond Young on information theory and network coding. This is chapter 9 of that book. So as we know, for a discrete memoryless channel with transition matrix given by P of y given x, channel capacity is given as maximum mutual information between the input x and the output y, and the maximization is taken over all input distribution. Here I am denoting the input distribution by R of x. X is the input to the channel and y is the output to the channel. Now as we know, this expression for channel capacity is what we call a single letter characterization. Now we know that this channel capacity depends on the transition matrix of the channel. It does not depend on the block length of the code used. And when the input alphabet size and the output alphabet size, that's finite, in that case this computation of this channel capacity is nothing but a finite dimensional maximization problem. Now we know that except for some simple specific cases, we do not have a closed form expression for channel capacity. So to compute channel capacity in general, we will have to resort to, let's say, a numerical computation or something like that. Now Blahut-Arimoto algorithm is an algorithm to iteratively compute the channel capacity and rate distortion function. Similarly, if we look at the rate distortion function, this is defined as minimum mutual information between the source alphabet and the reproduced alphabet, which is denoted by x hat, and this minimization is taken over all conditional distribution of q of x hat given x, such that the expected single letter distortion is less than some quantity d. So q of x is the conditional distribution and of x hat given x, and q of x hat denotes the joint distribution which satisfies the distortion constraint, which is given by this here. Okay. Now here also this is a single letter characterization. It does not depend on the block length of the rate distortion code. It only depends on the random variable x. So when the source alphabet and reproduced alphabet size is finite, again this becomes a finite dimensional minimization problem, and again here in most of the cases we do not have a closed form expression for the rate distortion function. So to compute rate distortion function, then we will have to resort to some sort of a numerical method. So this gives a motivation to study an iterative algorithm to compute this rate distortion function and channel capacity. So first let me talk about this algorithm in a general setting. So I'm going to talk about alternating optimization algorithm, and then we will come to the specifics of Blahut-Arimoto algorithm. So let's say you want to compute double supremum. So you have a function f over u1 and u2. U1 belongs to a convex set A1 and U2 belongs to a convex set A2. Now you want to compute a double supremum of this function f, which is a function of u1 and u2, and this function f is a real function defined over A1 cross A2. The function is also bounded from above. So this function is upper bounded by some quantity, finite quantity, and it is continuous. Also its partial derivatives, it has continuous partial derivatives defined. So these are the conditions on the function f. Now assume for all u2 belonging to this convex set A2, there exists a mapping C1 U2 which belongs to this convex set A1 such that f of C1 U2 and U2 is equal to maximization of this function f of U1 dash U2, where U1 dash belongs to this convex set A1. Similarly, let us assume that for all u1 belonging to this convex set A1, there exists a unique mapping C2 u1 which belongs to this convex set A2 such that this condition is satisfied, that f of u1 and C2 u1 is equal to maximizing of this function f of u1 and u2 dash, where u2 dash belongs to A2. So then we can write this double supremum problem as we are computing a supremum of f of u, where u is this, and we are computing this over u which belongs to this Cartesian product of A1 times A2. Now let us state the alternating optimization algorithm. So let's say at some time k, uk is given by u1k and u2k. So we start off with some initial at time k equal to 0, we start with initial value of u1 which I am denoting by u1 0. So let this be an arbitrarily chosen vector and it belongs to this convex set A1. Then u2 0 is given by C1 u1 0, and this belongs to this convex set A2. In general, for k greater than equal to 1, we can define this uk by u1k and u2k, where u1k is nothing but C1 of u2k minus 1 and u2k is C2 u1 of a time k. Now let this function f, which is basically this, at kth iteration, so we are denoting this value by this, is nothing but function f at kth iteration is f of uk, which is f of u1k and u2k. Now this is greater than or equal to f of u1k and u2k minus 1, which in turn is greater than f of u1k minus 1 and u2k minus 1. Now these two relations follow from these two properties. So we have this property and this property. So for all U2 belonging to A2, there exists a unique C1 U2 which belongs to this convex set A1 such that f of C1 U2 U2 is nothing but maximizing this function f of U1 dash U2 when f U1 dash belongs to A1. And similarly there exists for all U1 belonging to A1, there exists a unique C2 U1 such that this relation holds. So because of these two properties, we know that these two hold. Now, so what we have shown then is f of k, f as a function of k is basically a non-decreasing function. So f is a non-decreasing function. So f of k is a non-decreasing function, and remember it is bounded from above. That was one of the property of f of k. If you go back, this function f of f is bounded from above. Okay, so f of k is non-increasing but it is bounded from above. So what does that mean? It means that f of k must converge, must have a limit as k goes to very high. So f of k converges to some finite quantity. Now if we replace this function f by minus f, then in this problem, if we replace this f by minus f, what we get is a double infimum of this function f, where we have similar conditions that f has to be continuous, partial derivatives have to be continuous, f is bounded from below, then this double infimum can be computed also using this alternating optimization algorithm. Now this form we are going to use for computing the rate distortion function, whereas this form we are going to use to compute channel capacity. So let us first prove a lemma that we are going to use, and then we will state our Blahut-Arimoto algorithm for computation of channel capacity. So R of x is my input distribution and P of y given x is my transition probability. Now let R of x times P of y given x be the joint distribution on x and y such that R of x is greater than 0, so its R of x is strictly positive, and let Q be the transition matrix from y to x. Then what this lemma says is as follows: R of x multiplied by P of y given x log of Q of x by y divided by R of x. If we sum it over all x and y and we maximize over all q, then this is nothing but summation over all x and y of Rx Py of x log of q star x given y divided by Rx, where this q star of x given y is given by this expression, and this maximization is over all q such that q of x given y is 0 if and only if P of y given x is 0. Okay. So what we are saying is, if you try to maximize this over all q, then this is basically given by this expression, where the expression of q star is given here. Okay. So we are going to use the divergence inequality to prove this result. So let us see how we are going to prove this. Let Wy is given by this expression r of x prime p of y given x prime summation over all x prime. So this is nothing but this one, this term. Okay. Let us denote this by wy. Now, without loss of generality, we will assume that for all y, p of y given x is greater than or equal to 0 for some x, and since we will consider a strictly positive r, so r greater than 0, so then w of y will be greater than 0 for all y, and if w of y is greater than 0, you can go back and see if this is greater than 0 and these are greater than 0, then this will be also greater than 0. Now from this is my wy, right? So I can write wy times q star of x given y to be equal to r of x p of y given x. So that is what I am writing here. All right. Next, just recall, we want to show that if we maximize this over all q, this is given by this expression where q star is this, right. So the way we are going to show that this is the maximum value of this function maximized over q, we are going to prove this by showing that this minus value of this function for some other q, that is always greater than or equal to 0. If we can show that, then we have proved that q star x given y is the one that maximizes this function. So what we are going to show is this function evaluated at q star minus this function evaluated at q. Now this is, so if we take this is a common term, if we take this out, this is a common term here. If we take this out, we get log of q star x given y divided by r of x minus log of q of x given y divided by r of x. So this can be written as log of q star x given y by q of x given y. Now we just now showed that this term is nothing but wy times q star. So if we plug in that value here, we get this expression. Now this term does not depend on x, so let us bring it out. So we have this term summation over x and this term summation over y. Now you can see this particular term can be written as divergence of q star and q. Now we know that divergence between two distribution p and q is greater than or equal to 0, and since wy is also greater than 0, so this whole thing will be greater than or equal to 0. So then what we have shown is this function evaluated at q star that has the maximum value. So we have proved this result, this lemma, which says if you try to maximize this over all q, then this is the maximum value where q star is given by this expression. we state that for a discrete memoryless channel, the capacity is given by this expression, where maximization is taken over all q such that q of x given y is 0 if and only if p of y given x is 0. So let us prove this. So we will first consider a strictly positive distribution of R. Let mutual information between x and y, let us denote by I of Rp, where R is the input distribution and P is my channel transition probability. Now capacity can be given as maximum mutual information and maximization over all input distribution R. Now let R star achieves capacity, and if R star is greater than 0, then we can write this as maximizing mutual information to R greater than equal to 0. This becomes maximizing mutual information when R is greater than 0, and from the definition of mutual information we can write this as in this particular way. Okay, and this is nothing but supremum of R greater than 0 maximizing over q of this function. Now in case R star is not strictly positive, then since mutual information is continuous in R, so for any epsilon greater than 0 there exists a delta such that the Euclidean distance between R and R star is less than delta, then this relation holds that C capacity minus mutual information is less than epsilon. So in particular there exists an input distribution R tilde greater than 0 such that this relation holds. So capacity is given by maximizing the mutual information over all input distribution R. This can be written as this is greater than equal to supremum of Rp and supremum over all R greater than equal to 0, and since R tilde this can be written as greater than equal to mutual information between some distribution R tilde P, and since R tilde satisfies this relation, satisfies this condition, so we can write that this mutual information between R tilde P will be C minus epsilon. This last thing follows from the fact that there exists an R tilde which satisfies this equation. So we have this. Now if we let go epsilon to 0, we get the expression for capacity as this. Now let us see how we are going to use alternating optimization algorithm to compute the channel capacity. So first we are going to choose a strictly positive input distribution which I am denoting by R0. Of course this belongs to this convex set A1, and we define q of 0 or in general q of k by this relation. Why? If you recall, we have proved a lemma earlier, and this lemma is this. What does this lemma says? The maximum value of this function maximizing over all q is given by this, where q is given by this expression. So given an R, we should find q in this particular fashion, because this will maximize this function over all q. So this is how R and Q, they are related. So that's why we start off with some initial arbitrary input distribution which is strictly positive R0, and then we have to find Q0. For that we are going to use this. Now once you know Q0, you need to find R1. And how do we find R1? Or in general, for any k greater than equal to 1, we need to find R at time k. So we need to find an R which belongs to this convex set A1 that maximizes a function for a given Q. Now remember, in addition to maximizing this function, we also have some constraints on R. And what are those constraints? First one is sum of probabilities should be 1, and the probabilities are basically greater than 0. So these are the two constraints we have. So we want to find the optimal value of R given these two constraints. So how do we proceed? So we will take help of this method of Lagrange multiplier. So we will define this. This is my objective function. This is my constraint related to the fact the summation of this R of x is 1. Now at the moment I am ignoring this positivity constraint. That's because later on we will see then when we compute the value of R of x, that is already taken care of. So this is a Lagrangian. Now the next step is to find the optimal value. I differentiate it with respect to R of x. So when I differentiate with respect to R of x, I get this summation over y, p of y given x log of q given y minus log of R of x minus 1 minus lambda. Now when we equate this to 0 and when we collect terms, what we get is log of Rx is equal to summation over y, p of y given x log of q x given y minus 1 minus lambda. Or in other words, I can write R of x in this particular way. Now we need to find lambda, right? Now we know that summation of Rx of x over all x, that's equal to 1. So if we put in that constraint, we get the value of R of x to be this. Okay. Now note that here we are taking product over all y, here we are taking product over all y. We have this term which is greater than 0, we have this term which is greater than 0. So R of x is going to be greater than 0. So earlier we have not taken this positivity constraint, but you can see that R of x which comes out is positive, is greater than 0. So that is implicitly taken care of. Now, so this is the optimal value of R of x in terms of Q of x. Earlier we have computed the optimal value of Q of x in terms of R of x. So at kth iteration, basically I can write R of kx as product over all y q for k minus 1 time x given y raised to power p of y given x divided by summation of this. So note now, we started with an arbitrary strictly positive distribution of R, R0. We plug that in to get Q of 0. Now once we get Q of 0, we plug the value of Q of 0 here to get R of 1. Now once we get R of 1, we are going to make use of, once we know R of 1, we are going to make use of this expression to get Q of 1. Now once we get Q of 1, we will make use of this to get R of 2. So that's how we are proceeding. So this, you can see, this is an iterative way we are so these vectors Rk and Qk are defined in order. We first start with an arbitrary R of 0 which belongs to this convex set A1, and then we use R0 to compute Q0, then we use Q0 to compute R1, and so on. So you can see that each vector in the sequence is a function of previous vector except R of 0, initial value. Okay. Now I am not showing you the proof, but it can be shown that R of k belongs to this convex set A1 and Q of k belongs to this convex set A2. This can be proved using mathematical induction. Now once we determine R of k and Q of k, we evaluate the function f at kth iteration, which is given by this. Now the next obvious question is this function guaranteed to converge, and when will it converge? So when f is a concave function, this function will converge to the expression for capacity. So next we will show that this expression for channel capacity, this function is a concave function. So to show that this algorithm converges to channel capacity, we are going to show that this function that we evaluated, this is a concave function of R and Q. So let us consider two ordered pair R1 Q1 and R2 Q2, and let lambda be a variable between 0 and 1. Now using log sum inequality, we can write lambda times R1 x plus 1 minus lambda times R2 x log of lambda times R1 x plus 1 minus lambda times R2 x divided by lambda times Q1 x given y plus 1 minus lambda times Q2 x given y. This is less than equal to lambda times R1 x log of R1 x by Q1 x given y plus 1 minus lambda times R2 x log of R2 x divided by Q2 x given y. So this follows from log sum inequality. Now we are going to take the reciprocal, so reciprocals of these logs. So what you will notice is, so what I did was I just took a reciprocal of these log terms. If you take reciprocals of this log term, this less than equal to term will become greater than equal to, and that's what happened here. So I took the reciprocals of the logarithm. So then this log of this by this is now greater than equal to lambda times R1x log of Q1 divided by R1 plus 1 minus lambda R2 log of Q2 R2. So I essentially took reciprocals of these log terms, and this term which was earlier less than equal to is now greater than equal to. Next I multiply both sides by P of y given x and sum over all x and y. So if I do that, what I get on the left hand side is function evaluated at lambda times r1 plus 1 minus lambda times r2 and lambda times q1 plus 1 minus lambda times q2 is greater than or equal to lambda times function evaluated at r1 q1 plus 1 minus lambda times function evaluated at r2 q2. And we know from the definition of concavity that if function evaluated at this is greater than or equal to expected value of the function, basically this is the condition for concavity. So this shows that the function f is a concave function. So hence we have shown that when we iteratively compute r and q, as k increases, basically f evaluated at kth iteration will tend towards the expression for channel capacity, and this is Blahut-Arimoto algorithm for computation of channel capacity. Now Blahut-Arimoto algorithm for rate distortion function is very similar. We will just quickly browse over the results. So we know the rate distortion function looks like this. Typically something like this. You have, this is rate, this is distortion, so this is maximum distortion, d max. So R0 typically greater than or equal to 0, or otherwise R0, Rd is 0 for d greater than 0. It is typically a strictly decreasing function, as we saw. Basically R of d typically is like this or something like that. Now we also know that this rate distortion function is a convex function. So then for any s which is negative, there exists a point on this rate distortion curve for d between 0 to d max such that the slope of the tangent to the rate distortion curve at that point is equal to the slope s. So what I am saying is, if you have a rate distortion function, let us say something like this, this is my d max. So there exists a point on this rate distortion curve such that the slope of the tangent to this curve at that point is equal to s. Something else here. And let us denote this point as, so this is my d of s and this is my r of d of s. For s less than 0, the tangent to the rate distortion function has slope s and its y-intercept is given by r of ds minus s times ds. Now let IPQ denotes the mutual information between x and x hat, and DPQ denotes the expected distortion, where P is the distribution for x and Q is the transition matrix from x to x hat. For any Q, then this is a point in this rate distortion region, and the line with slope s is going to pass through this point. So this will give a y-intercept of this. Now since this rate distortion curve defines the boundary of the rate distortion region, we can write this as minimizing mutual information minus S time this distortion, minimizing over Q. So for each S less than equal to 0, we can find a Q of x such that this is minimized. So we can find a QS that will achieve this minimum value. So then a line passing through this point is going to give me a tight lower bound on the RD curve. And if I do this for all S's, I essentially can trace out this rate distortion curve. Okay. Now let us talk about an iterative way to compute the same. So without proving, I am just stating the lemma that I am going to use. The proof of this lemma is all on the similar lines as the proof that we did for lemma for computation of channel capacity. So let P of x, Q of x hat given x be the joint distribution on x and x hat such that Q is strictly positive and T is a distribution on x hat such that T is also strictly positive. Then minimizing this over all T is given by this expression where T star is this. Now again, this proof is very similar to, we can use divergence inequality to prove this result. I am not stating it here again. Again very similar to the proof that we did for channel capacity. So if now this is mutual information and this is my distortion. So basically R of ds minus S of d, which is nothing but minimizing this over all Q. Now this mutual information is given by this and this is given by this term. Okay. So then I can write R of ds minus S of ds is basically this term. Now we are going to use alternative minimization algorithm to compute this. So we start with a strictly positive matrix Q of 0. The next step is we need to find T at time at iteration index k, and this is given by this. Now this follows from the lemma that minimum value of this minimum over all T is given by this, where the value of T star is given by this expression. So given a Q, you know what is the next T. Now once you find T, you need to then next find Q of 1 at Q at index iteration index 1. Now how do I find Q in general for k? Again this process is very similar to what we did. We want to maximize this with some constraints, and what are these constraints? We have this positivity constraint, Q of x hat given x is greater than 0, and we have the sum of probabilities adding up to 1. So we will again follow the method of Lagrange. So we will form the Lagrangian objective function plus lambda times this constraint. We will initially ignore the positivity constraint, and later on we will show that Q comes out to be positive. So that condition is explicitly taken care. So without showing you the details of this expression, I am just directly writing the expression for Q for iteration index k. And again, this is exactly same procedure that we followed for when we computed R of at some iteration index x for computation of channel capacity. So then if there exists a point R of ds on this rate distortion curve such that the slope of the tangent at that point is equal to s, then what we will see is as k increases, this converges to R of ds and ds, and if otherwise you will see that this term will be arbitrarily close to a segment on this rate distortion curve where slope is equal to s when k is sufficiently large. And the condition for convergence is, so this function has to be convex function. So I am not proving this, again very similar proof to what we did for the computation of channel capacity. So to summarize, we have given to example 1 for the case of computation of channel capacity, we have shown how we can iteratively compute it, and similarly for the rate distortion function, as we said, we initially start off with some strictly positive value of q of 0, and then we use that to compute t of 0, and then we use t of 0 to compute q of 1, and we process that in an iterative fashion to compute the rate distortion function. So with this I will conclude this lecture. Thank you.